Continuing with the program, we have the honor to have Dr. Oscar Castillo. He is a professor and researcher at Tijuana Institute of Technology, where he leads the Hybrid Intelligent Systems Research Group. He holds a Doctorate in Science degree from the Polish Academy of Sciences and is a Level 3 Emeritus member of Mexico's National Research System. He currently serves as president of the Hispanic American Fuzzy Systems Association, past president of IFSA, and chair of the IEEE Computational Intelligence Society Mexican chapter. His research focuses on Type 2 and Type 3 fuzzy logic, fuzzy control, and hybrid computational intelligence. Without further introduction, Dr. Oscar Castillo.
Okay, so I would like to thank the organizers for inviting me to deliver this talk, and thank you for the attending people here. And I will talk about some of the things I have done in my area. So this is a summary of my work, and from this year, I'm a profesor emérito del Sistema Nacional de Investigadores, and that doesn't mean that I'm old. Like I was talking to Cristina, one of our students, and she was saying that if we were retired, and I told her that if we are working very hard in our research, we don't notice these ages, this thing like the age. Okay, so let me talk about very quickly about fuzzy. So all mathematics based on numbers is what could be called type 0 in this categorization. So Professor Sade introduced in 1965 fuzzy sets. Now we call those sets that he proposed type 1 fuzzy sets because it's the lowest level of fuzzy. And later himself, he did propose type 2 in 1975 because he noticed that actually his goal of representing uncertainty was not achieved by type 1 because it was very basic idea. I will show you very quickly and briefly in a few minutes. And so he proposed it, although almost nobody took this idea seriously at that moment until Professor Mendel in 1999, when he tried to start developing this type 2 idea. So most people remember or recall Mendel as the type 2 important people in this area, although Professor Sade, he did propose them initially in 1975. So anyway, now at this stage, we know that interval type 2, general type 2, which are two different kinds of type 2, are useful and can do a good job in some applications. And so it's not something that is new, but what we have is the problem of designing this kind of a system, like Professor Melin was talking about designing a neural network, but also we need to design an optimal fuzzy system for an application, and for that we use bio-inspired or meta-heuristic algorithms. But still we have many problems that even with those tools are not sufficient. That's why we still do research theoretically on other kinds of fuzzy and other kinds of methods, intelligent methods. And also more recently, quantum fuzzy inference has been introduced and has been tried in applications with good results. So there are many things that could be still done in this area. Anyway, if we do research on Scopus, so the publications that have been done through the years, we see that in this intersection between quantum and fuzzy, there have been increasing number of works, and some of the authors. And Giovanni Campora from Italy, he was our keynote in our conference in August from Italy. He is one of the people in this top 10 list of researchers. He has applied quantum fuzzy inference to controlling the particle accelerator in Switzerland with some of his students, and also controlling inverted pendulum and other applications. So it's, I think, promising. We are starting in our work, at least at this point, to consider this idea in some applications. Anyway, these are the main universities on this area. We believe in a few years maybe our universities will be in some of these top 10. Anyway, type 1 is an idea proposed by Sade. So actually, what he did was propose to extend the original concept of sets, classical sets, coming from the Greeks more than 2,000 years ago, have been using mathematics for more than 2,000 years. So anyway, why this is the case? It's another story, another talk. So anyway, he proposed to extend to having membership between 0 and 1. Any value between 0 and 1, although this was good, is not sufficient to describe uncertainty. This was demonstrated by Clear and Yuan. And this is the classical way of having a type 1 membership function. This is a triangular. So for a particular height in meters, the membership to this set of tall people will be this, if this is the correct membership function, of course. Anyway, so the idea is that concepts, natural language words, could be given a fuzzy set to give them an interpretation, or the semantics will be given by the fuzzy sets. This is the general idea. So if this is the correct fuzzy set for representing the uncertainty of the concept of tall, for this height, this will be the membership. So this is just a simple example. But this is not sufficient because different people view this differently. So for you maybe taller people will be considered really tall for you, and for other people not. So anyway, so that take us to the concept of type 2, because in this way we will represent the different meaning for different people. So we will have like an array of type 1 membership functions representing the type 2. So interval type 2 is like this. You have this footprint of uncertainty, this area representing an infinite number of type 1s contained inside this triangular type 2 membership function. The footprint of uncertainty pho represents this family of type 1s contained inside between the lower and the upper membership function. So this is an interval type 2 fuzzy set, which will be a better approximation to represent the uncertainty of this concept of tall in real life. So people work with this in natural language problems because you can use fuzzy sets to represent words. That's another area, I will not work on that. But anyway, this is the idea. And so, but this comes with a complication of, obviously, higher level models come with more computational complexity. So actually, for computing interval type 2 fuzzy sets, we need to consider the family of embedded fuzzy sets contained inside. But fortunately, Mendel and Liu showed that 2 type 1s are sufficient to approximate an interval type 2 with the concept of switch point. And basically, here is the idea very quickly. You need to have the red one, which is a part of the upper, and you switch to the lower, and then part of the lower, and you switch to the upper, the green and red ones. These 2 type 1, special type 1s, will be, if we find them, sufficient to approximate on average the interval type 2, approximately to a certain level. So in this way, the complexity only increases 2 times the time you need for type 1. That's the advantage. But you need to find these switch points, and this is an optimization problem. They found, fortunately, an iterative method that in applications 3 to 4 steps will give us these switch points, and then around 2001, it was sufficient to implement controllers in real time, and also doing hardware implementation was faster. And so that was very important, because if not, it was too complex to do in real problems in real time, mostly in control. For robotics, for example, it was not possible to compute it with interval type 2 if we didn't have that. Anyway, this is the general architecture of type 2. Basically, if you have seen fuzzy systems, you have a course in fuzzy system, it's very similar to type 1. Just here at the output, we have a type reducer, because we will have inputs, numerical inputs, fuzzified with membership functions. Then we have the fuzzy rules, and we have the inference. The result will be type 2, so we need to reduce it to type 1, and then we will defuzzify. Although right now, more modern methods do these 2 processes in the same step. There are some direct calculations of the results of type 2 that avoid type reduction, but in any case, historically, this is important because you see that we need an extra computational part here that carries a burden, computationally speaking. So that's why interval type 2 is more demanding. But now with the method we have is still linear. So computing type 1 is linear. We have just a factor of 2 over the linear algorithm that is having in type 1, so it's not too much. Anyway, there's one more step, because this is not the complete thing. Although it's an advancement, or it's an improvement, we need for type 2 to have a complete type 1 fuzzy set for each point in the original type 1. So in this case, we have like a primary domain and a secondary domain, and a primary variable and a secondary. And so in this sense, what we have now is in 3D, because on this plane is like before in interval type 2. For each point, we will have an interval representing the membership, but now we have a complete triangular. So in this case, for each point in this interval, the secondary membership is not fixed. In interval type 2, the secondary membership is fixed to 1, constant. So it's like an approximation in between type 1 and real type 2, general type 2. And so this, of course, carries more computation, because what we do is slice it horizontally, for example, and each slice is like an interval type 2. And so if we sample this 3D membership function in this case, but with 100 points, we will have to compute 100 interval type 2s to approximate a general type 2. So it's more complex. And so that originated that before maybe 2017, 2018, real-time general type 2 was not possible. Computing at least in PCs in our labs, it was not possible. So real-time control of a robot was not possible. But now, with better algorithms and better computers, we can do it real-time in no problem. So that's the trend in this area, and in other areas, of course, in artificial intelligence. Anyway, mathematically speaking, it's more interesting because you have more things to view, and I will not go into that because I can say that all mathematics can be generalized with this idea, because actually you are changing the sets. And then you have operations on fuzzy sets, then you have functions, relations, differential equations, integrals, all of that is generalized to fuzzy. And also statistics and probability can be fuzzy probability, fuzzy statistics, and so on. So mathematical side I will put aside because it's not the main thing here. And so I will go only on to computing side, but it's interesting to also see that evolution, because maybe in the future mathematics will teach to our children, or to students will be fuzzy mathematics or something like similar to that, because there are other generalizations that have been proposed also. Anyway, so the beginning, around 2001 to 2010, most of our colleagues and us, we were trying to show that type 2 could be better. Because if not, there are many generalizations that are proposed theoretically that at the end do not work, or for the moment they are not working on real problems. And so at that time we were working. I remember Roberto Sepulveda and Oscar Montiel were my students, and this was from one of our papers published 2008 or 9, I don't remember. And we showed that type 2 was able to beat type 1 in control under noisy conditions. So basically, we were comparing on the left, you can see the type 1 membership functions for control, and on the right, the interval type 2. This is for the error, change of the error, classical inputs in control. And the output, you can imagine controlling velocity, so error and velocity, change of error in velocity, and the variable that you use to control the car, for example, or the robot. And on the right, these are interval type 2, the same form, centered around the type 1s, just perturbed to have a footprint. Anyway, this is the situation, this is the controller, this is the plant. We have this mathematical model for the plant. And the output is measured here, the observable variable. And we feed back to the input to compare it to the reference or the desired value. And this gives us the error, and then the error with the previous error, the change of the error. But we have noise. We assume here the noise in the sending the signal here as in this way. And we did compare with the metrics usually using control like these ones. And if there were no noise in the feedback ideal situation, we compared it and there was almost no difference. But if we use the noise, assume that there was noise in this case, then we will see the difference. So here is not uncertain, not assuming that there is no uncertainty in this case on the feedback, which is not realistic, but anyway, we did it in simulation, we could do it. And no difference, red one is type 2, blue one is type 1, almost differences, but not too much. But if there were noise in the feedback, in this case, you can see very clearly in this metric is very clear. The blue one is the type 1 and the red one is the type 2. If you sum the errors over 200 seconds in the simulation, very different, very significant difference between the errors of control in type 2, which are significantly lower. And if we change the level of noise, because it was for a particular level of noise, higher levels of noise will show bigger differences, lower levels will type 2 tends to be like type 1. So we were expecting, that was our hypothesis, and we verified it, and this was one of the first papers showing this in real. Then after that, simulation, then after that we did with real systems. Anyway, we applied this concept. You saw Professor Melin's talk a few moments ago. You notice that we use also fuzzy systems to control the algorithms, to control the meta-heuristic algorithms that do the optimization. And so we have done that. This is just very quickly to show how we have done this for several algorithms, but this is particular case, the bee colony optimization algorithm. My student, Gloria Madorci, did that around 5 years ago when she finished the doctoral program. She actually controlled the bee colony parameters during execution by using a type 2 fuzzy system, and also applied that fuzzy bee colony, which you can call it, to optimize the controller of a robot. So actually she was moving or controlling two things. One was the parameters of the bee colony with a fuzzy system, and another thing was that was applied to controlling, to finding the parameters of the controller of the robot. Anyway, so bee colony, I will show you some details of that very quickly. This is the plots for a general type 2 memory chip. I think I didn't show that before in 3D. And you can see it from the top. And we show it with different shades of or tones of color, I mean, to see that, to get the idea of the 3D form. And anyway, you slice it horizontally to have interval type 2s, I told you before. And this is the controller of the robot with two wheels, two-wheel robot. These are the errors and the control of the torques of the two wheels. And this is the kind of robot. And these are the rules. We did have this previously from other works in type 1. So these are 9 fuzzy rules to control the two wheels of the robot to make it move around. And what my student did was she did study, and so she could understand the bee colony algorithm. And actually, these are the main equations of the bee colony optimization algorithm. And the main parameters here are alpha and beta that determine how the probabilities for moving to one point or another are used. And depending on alpha and beta, these changes in the iterations are more are higher or lower. And so that's what she wanted to control, because in actually many people just use alpha and beta fixed to 1 or some value. And so if you leave it like that, it could take more time or could not find something good. But if you change it according to what you are obtaining at each moment, then it could improve at least faster convergence. And so basically, iteration is viewed as a fuzzy variable here. Iteration actually is a number, but You can view it as iteration low, medium, high, in this case as fuzzy. And diversity, of because you use a population of bees, different bees are trying to find that solution, like finding food in this case. And diversity is a number, but you can view it also as high, medium, low. And you can, if you understand the algorithm, you can find the rules to control the alpha and beta so that the algorithm improves convergence. So actually here are the membership functions for iterations and diversity, and also for beta and alpha, the values that are obtained. And of course, this after the classification gives you the particular number that is used in the algorithm. So of course the algorithm increases computation because you have to do that each iteration is computed, but we of course try to see that this is not too much. And of course sometimes these more calculations are giving you results in less iterations. So in some way you can have a trade-off so that it's not too much time. Anyway, this is for interval type 2 and for general type 2. You can see the difference in the membership functions. And what she did, she studied the algorithm and she found that these 9 fuzzy rules control alpha and beta so that you can improve the convergence. Of course, you can imagine many experiments that she did. And these are the fuzzy rules. Like in this case, will be like the knowledge about the algorithm. She understands the algorithm and she put the knowledge of the algorithm in these 9 fuzzy rules. And these are experiments. I'm skipping many parts because it's not too much time. But the robot was that she was simulating was trying to follow trajectory, the red trajectory. And the desired one is that what we call it. The actual robot trajectory is the blue one. So this is with one of the, you know, this BCO is a stochastic algorithm. So you actually perform many experiments and do averages. But this is one of the cases of that those 30 experiments that she did. Anyway, this is one of the optimizations with the without noise of the original algorithm. And sorry, this is with the original algorithm, and this is with type 2, general type 2 algorithm. So the errors were found to be lower between the actual behavior of the robot and the system, and these are. But on average, without noise, there is no difference. With noise, there is actually some difference, and these are with noise, and you can see how the original bee colony finds, for example, this trajectory for the robot, the blue one. But with type 1 is a little better, and with interval type 2 more, and general type 2 even more. And now she has done it with type 3 also, but I'm not showing here this. Anyway, now this is part of the work with other my students. Felizardo, he was here. He's better. And he experimented with the omnidirectional mobile robot we have in our lab. And these are the questions of the robot, which is more difficult than a robot of 2 wheels or 2 tires, because here we can have translation not only the regular motion of the robot with the tires. So anyway, this is the kind of robot. And in this case, the architecture for the controller is like this. We have the sensors as inputs, the information of sensors, and the outputs are the linear and angular velocities or speeds. This is for interval type 2. Here are the actual memory functions that he did find. Initially, he did a manual design. Even with that, he was able to have good results. And later, he optimized with some algorithms, metaheuristic algorithms. These are the interval type 2 membership functions. These are for the outputs. And this is in simulation because this robot that we have is from Festo, and they have a simulation environment. You can test your robot before doing the actual physical test in the robot. And in simulation, you can see the behavior before doing that. And we can see that we can find lower times and higher velocities with the type 2 controller because you can move better in a circuit. And the errors for a particular trajectory are lower. And also, he did that all for general type 2, and we have to still test that for type 3 in our work. Now, for type 3, but we go one step further. we can, before we had in type 2 primary membership, secondary membership. Now we have a tertiary membership function, which measures the uncertainty over the secondary, as before the secondary measures the uncertainty over the primary. So in general, there are papers on type N, theoretically, because you can do the same thing again and again and again. Until what level is sufficient for a particular application depends on the complexity of the problem. Of course, that's another thing. Anyway, now we are at the stage when we, because of computational resources, we use this fixed to 1, so we actually have interval type 3. So this tertiary is fixed to 1 like before. The secondary was fixed to 1 in interval type 2. And we have done some, this is the view of the membership functions. The footprint will be constructed or built with these green parts. And these are the operations. So we have a book on this where we have proposed the mathematical equations for doing operations of this, and also the programs to plot these things. And we have seen improvements because for levels, higher levels of noise or more uncertainty in the problem, you can have better results than type 2. And actually the difference is that interval type 3 has interval type 2s in the secondary, while on the other hand, you have interval type 1s in general type 2. This is a particular real application for controlling temperature that I did with some colleagues, and it has shown that type 3 could outperform type 2 and type 1 in controlling temperature. Real was published in Journal of Fuzzy Systems. And this is for controlling microgrids in another publication. Also for quality control, I was remembering seeing the presentation by Kenya. We have done quality control with fuzzy systems, actually for tomato quality, about 20 years ago. And I was wondering, but I could not ask a question about that. Why if you have tested quality fuzzy rules for quality evaluation or not for that case? Maybe combination of that. I don't know if it will work for cucumber. Yeah. Anyway, this is for production of sound speakers. We did it before many years ago with type 1, then with type 2, and now we tested with type 3 to see the results. And this is the bee colony with type 3 that I was explaining type 2 a few minutes ago. And now, what we can find on quantum inference. There are many things here because they achieve better results, but my question, philosophically speaking, is why? Why, if we introduce the quantum part previous to the falsification, is what they're doing, why this improved results? Well, we could talk about that on some break or another place. But in any case, if this is possible, we could try it. But why it's happening? In some part, I think is because it's the uncertainty, fuzzy managed uncertainty, although it's semantic uncertainty. But the uncertainty coming from quantum is probabilistic, I think, in some way. So maybe if this is mixing some problems, it could work. Maybe it's that's the case. I'm not sure. But in any case, and also the systems at the level, atomic level, maybe the quantum mechanics at that level affect the results. I'm not sure. So it's I think to do research on that. Anyway, so I have seen papers on quantum fuzzy control of inverted pendulums that do better work than without quantum. So, but the reason, the theoretical reason why is I'm not sure why this is true. And also here I show you the one I did understand more quickly. This is not mine, but this is well, this is quantum fuzzy inference. But this was very easy application of edge detection. You have seen edge detection to find the edges of the image, and they did it. And they did find it's almost same result here. You can those of the right are classical methods. So actually fuzzy, even some papers from Professor Melin on type 2 fuzzy edge detection were done many years ago. And they show that type 2 beat type 1 fuzzy edge detection. But with quantum, they compare to type 1 and they have good results. And this is the figure showing the almost same fuzzy classic, fuzzy quantum in this case. And so here is my my vision of the future. At least for me or for my group, maybe for you, because Professor Montiel worked in fuzzy many years ago. Okay. Okay, so we will have to talk about that. Uh-huh. So yeah, so we will have to see. Apparently, the paper, maybe in the system of controlling the particle accelerator of that they did with Giovanni Campora, maybe the problem is very complex, and so that's why they have good results. And maybe lower level it will not be so significant. I don't know, but we will have to see how it will be. But in general, if it is possible that it could improve, we could have. I talked about to him about interval type 2. He actually did a conference paper on quantum interval type 2 in FAST, IEEE this year, but not journal paper yet, so maybe he has not sufficiently good results. Anyway, you could combine, and in theory also, I have seen some quantum type fuzzy neuro, so fuzzy neural networks with quantum, so also that's something that to consider. So anyway, I maybe have said many things, but if you have questions, these are some of my books, and this is for type 3. So if you have any questions, you can ask me, and maybe I don't have, maybe for quantum I will not have the definite answers, but maybe my idea I can give you on this.